Hello! Hello! Who's out there? Hello, welcome. It's chemistry time. I've missed chemistry time. I hope you've missed chemistry time too. It's a shame I haven't had much chemistry stuff to work with until, again, one day Providence just drops something in my lap and it's like, oh, okay, it is now time to do chemistry reacting stuff. It's partially actually fueled by the fact that or the lack of chemistry content is partially fueled by the fact that for reasons the the current government is actually shuttering the US CSB as much as possible. You know, the fun somebody died in a lab explosion or a factory explosion kind of vids. So yeah, that sucks for many reasons, and least of which being that I don't have more content to react to and watch anymore. So like, I'm pretty much dependent on Explosions&Fire and Nile Red actually uploading stuff to react to, unless I find more chemistry YouTubers. I mean, I have found more, but they typically only do like 10-minute stuff rather than like a good solid 30+ minute thing that I could drag out into at least an hour by saying, oh, yo, hold on, this chemistry is dope. Let me write it all down. So, yeah, a little bit disappointing. Though I do have something else in the back pocket here in case the, well, not in case, but, well, sort of in case. If I have extra time and feel like everyone feels like we should keep going, I not only have this cool lead chemistry video, but I do also have another video on making some really strong nitric acid that's been in my watch later for a little while, and I think that might be interesting, because usually strong nitric acid creation comes with demonstrations of using it to, like, burn gloves and paper, because it's just that ridiculously oxidizing. But anyways, I think I should stop delaying the point and actually get to streaming and stuff, right? I guess I've also never done this before, but for anybody curious as to what the background, stream background music is, not only do I have my playlist for the stream background music when I need it like this in the description, if you want to go just check out what I think is good stream music, but I guess the three things that we were hearing right now is started with Powered by Lava Sonic Spinball Remix by Amasuke Audio, then Swingin' Swamp from Dungeons of Dreadmore, and then right now we have an AJ Despirito remix of Earthbound Your Name Please, which all these are very good musics in my opinion. I like them for the kind of just, you know, vibe and a half kind of feeling they give you. You can listen to them directly, but they're also not super distracting if somebody's talking over it, you know? Your brain can compete for both things at the same time. Anyways, I said I would stop stalling like a minute and a half ago, so I think I should stop stalling for real now and actually get on over to the content, so let's do that. Alright, and the stream layout's working good, cool. Barely had time to test it before today, but it's been a while since I've used the two streams layout, so I was a little concerned I might not get things to work right. But anyways, let's go look at some lead. I love lead. Not only is there lead here, though, there's also cesium and bromide. I also love cesium. You might remember it as that one chemical in the far left corner of the periodic table that is like, oh, if you throw this in water, like, there's gonna be a big explosion. So
G'day, this is Extractions&Ire, and welcome back to
audio
my shed
bounce.
in my backyard for some more lead-based entertainment. Today, we want to make some more cool glowy things. So we want to make
glowy
perovskite nanocrystals, and they'll be highly fluorescent under UV light if we can get it right. Yep. So we've got this bulk.
Oh yeah, I guess as a little bit of a primer, I usually do a little explaining. That's a very good, it's a very good frame to stop on. So let's see. So he's going to be making nanocrystals, so you can already imagine very small stuff. The other words he's saying are perovskite, which refers to a specific structure of compounds. It is complicated to draw everything out. In fact, it might be easier if I just search up an image real quick. I can just paste that into the little secondary window over there. It was perovskites were something that I had to spend a hell of a lot of time learning about in undergraduate chemistry because of just how prominent they were becoming in like modern research, and like the importance of like them for like use in solar cells and other kind of light capture applications, and just like here, some fluorescent stuff. Also, superconductors also are typically made using perovskites. So, like, yeah. Oh, well, hold on a second. That is not very zoomed in, or it's too zoomed in. There we go. All right, so this is the general structure of a perovskite. We have a very large positive cation of some kind in the middle here, which is surrounded by a bunch of and this specific example is strontium titanium oxide, but you can have different kinds of atoms in here, different elements. The strontium's a very big positively charged ion. The titaniums in this serve the role of a very small, somewhat small positively charged ion. And then the connecting bits between all the red dots are oxygens, which serve the role of a very small anion, meaning negatively charged. So all of this is a kind of complex way to say that you have a structure that balances out its negative charges of oxygens with two different types of element and elemental ion, and they are different in size, which results in this kind of caged structure for the very big ion in the center versus the smaller positive ions that are in the center of each octahedron rather than the center of a cluster of octahedra. But yeah, so they're doing that, and Tom over here is going to show us how it works and how he's getting to a fluorescent one that uses lead. I love lead. And yeah, I'll keep chiming in as necessary.
Perovskite, which is this lead-based semiconductor material, and we're going to grind it down to make these tiny crystals, which should be very bright under the UV light. If that works, we're going to try and see if we can change their emission color by changing the material.
I get the feeling he's not going to get them so perfectly round like that.
If we can make the nice green fluorescent material out of this cesium-lead-bromide, then maybe we can make a red cesium-lead iodide and a more blue cesium-lead chloride. So that's
and different halogens too. Okay, that makes sense.
Perovskite and nanocrystals. Our starting point is this cesium-lead-bromide, which we made, nearly a whole year ago in an episode where we tried to make big crystals of cesium-lead-bromide.
Oh, wait, yeah. This is like one of the first things I reacted to. Forgot about that.
I can't remember. Actually, if it was a whole year ago, does that mean the birds are going to come back? The birds might come back. Don't get me wrong, I do love the birds, but it's just a bit concerning to have baby birds around when you're doing lead chemistry. When we previously
it bioaccumulates, but like, can't be anything worse than what the factories are doing.
A certain chemical to continue on with this nanocrystal synthesis following this paper from, I think it's 2017. I now have some oleamine, so we can finish and see if we can finally successfully make these nanocrystals. But before we get into the practical aspects, I always find it's easier to appreciate the synthesis if we have an understanding of what we're actually really trying to do.
Oh god, no, science.
I know. We're going to speed run this. Some solids in the world are conductors, right? So
yeah, unfortunately, Tom, I'm going to turn this into an anti-speed run. Sorry, everybody.
Electrons are all shared between all the atoms in the ladder. Some materials are insulators, so the electrons aren't shared between the atoms, so they don't conduct electricity. And then you've got the secret third class of materials, which are semiconductors. Normally insulators, you can excite an electron, and now that electron is in the conduction band and can move around. When we've displaced this electron, we've got, now a positive charge and the negative electron. They are attracted to each other. When the negative charge recombines with the positive charge, we then release light back out again.
I always found that, again, another good frame to pause on. That kind of explanation is a little bit like hard to follow in some aspects, but just to summarize, conductors, i.e. stuff like metals, they have electrons just flowing everywhere freely around all of the positive nuclear cores of every atom. Insulators don't. It's just a bunch of different molecules and atoms all bound close together, but their electrons are not free to move. And the semiconductors are interesting where they kind of start off in that kind of insulator state, but when you excite them with either enough heat or electricity, or, well, not usually electricity, excite them with heat or light, they will basically absorb that light, send electrons up to a very high energy state, where that high energy state of electron can actually move around the entirety of the metal, or the entirety of the semiconductor. And meanwhile, all the other lower energy ones cannot. And then eventually, for this specific application where we're getting fluorescent semiconductors, the electron that was freely moving around and having fun will eventually settle back down into its place and release light at a slightly different energy, lower energy, because of it like used some of that energy moving around and bumping into shit. And that's the fundamentals of what is going to go on with this structure.
These perovskite crystals are a semiconductor, but if we put UV light on it, we don't get any fluorescence light back out again. So a much more technical question is, why does making these crystals small make them fluorescent when they're big, they don't fluoresce at all? The first thing we've got to do is just get rid of this model. I hate these diagrams with the dots and the circles. It's weird to think about exciting an electron in this diagram because you're kind of like, well, where's it going? You can put it somewhere else in the diagram to kind of show that it's
Yeah,
excited,
but that's not accurate.
Where, like, geometrically is the electron and how does it...
Yeah, so that's kind of something that I was alluding to a little bit with like the electron actually going to like a high energy level rather than like a space in reality. Because this is gonna really start recalling like this is gonna require me to recall some shit that I have not recalled since like undergrad. But you basically end up having let's see. Semiconductors have these, well, I guess all materials, but semiconductors have this, in particular, have like these bands, what are called electron bands. So if you remember maybe from me talking about things previously, when you have like, just say two atoms bonded, they will form molecular orbitals, being like the original orbital, which is where the shape, the probable cloud that the electron lies in. These would be these circles, the orbitals. They combine, and hydrogen brings an electron to the table, and you end up getting a bonding orbital, which is basically just the combination of those two spheres overlapping to form like kind of a big oval shape. Electrons will reside there. And then you have the anti-bonding orbital, which is the spheres not combining. And these are just kind of illustrations of quantum physics and work, them not really wanting to join together very much. So a similar concept still applies here. I'll just cut and paste that in a different layer so I can preserve it for later. So a similar concept still applies when you have big bulk materials rather than just individual atoms. But instead of having individual like bonding and anti-bonding molecular orbitals, you will end up having big collections of orbitals that are very similar in energy, and we call those electron bands. And in a semiconductor, or I guess technically insulators, but insulators have like way too big of a gap here. You'll have like a gap where at the bottom this is filled with electrons. I'll just shade that in to kind of represent that. Actually, it's shaded in with gray, a nice gray color. Okay, and then we can say text full of electrons. Full of electrons, make this larger. Full of electrons, right. And so when you add light to it, you can basically cause a couple of electrons, light being represented by H nu, which is a description of the energy of the light. You basically cause some electrons to jump up here into this so-called conduction band. Conduction band, which is kind of that space where because there are so many molecular orbitals available, and it basically amounts to having all of these like kind of spaces strewn throughout the bulk solid, and that means that the electron kind of has that free space to roam around and can just go between all of these orbitals without basically spending that much energy. You end up having the electron can suddenly now conduct around and conduct electricity. It's a moving charge. It's not locked in anymore. So yeah, that's more how it works rather than this kind of like thinking of just literal movement to another space. It is sort of literally moving to another space, but it's just easier to think in terms of, well, it's at high energy. And at this higher energy, there's a lot of empty possibilities of like places it could be, and therefore it can kind of move around at will when you apply electric current or something like that to it. Okay, that was probably belabored enough, and he's probably going to say the same exact thing now, but I had to say it myself because I need to tell you all that I know chemistry.
I find it's easier in this context to think of electrons as probability clouds, right? So what you're doing when you're exciting an electron is that you're changing its 3D geometry. We're obviously just going to depict this in 2D, but in semiconductor material, what we're doing is we're taking say, an insulating sort of isolated geometry. We're exciting that electron. The electron geometry, the potential is changing. So
the
now
electron
it
turns green
with the other atoms. So now it can freely move. That potential can be sort of shifted across to this same potential, but over different atoms. This excited electron, which is now in the conduction band and is free to move around, is still attracted to the place that it left behind. In this case, it's called a hole rather than a positive charge. It's kind of an absence of an electron. It's a whole thing. I'm not going to get into it. It's a whole thing. Oh, good bit. No.
Yeah, I mean, it's called a hole typically in this kind of work. It is literally just meant to refer to the electron is no longer here, and it is not a formal part, and it has some positive charge left over because the electron normally balances out the positive charge of the nucleus. Now it's out there, it's wandering about, it's not at its home, therefore it kind of left a hole behind. It wants to, the charges of opposite attracts makes it want to go back there, but the high energy of the electron and other nuclear forces kind of, also pull it away. It will eventually go back there, but it does not stay, does not rush. It's in no rush to return home.
Ideally, in our case, we want this electron to come back and interact with the hole, and then we get our light back out of again. But actually, fluorescence is kind of a random process. It's statistically random on, a one electron scale. So really, it does take time. The electron is free to move, so it just pisses off, right? Even though it's kind of attracted to that, it can go, right? And if it goes away, it can find other things to interact with, whether it's the surface of the crystal or a defect or just sort of lattice vibrations, can basically take the energy out of the system. So we don't get it back as light. So even though we have this charge separation, we end up with no fluorescence. So this is what's happening in the bulk state. And I will note, if you're trying to make solar panels, this is actually a really good thing because you want this electron to piss off from the hole because you want this electron to go all the way out the material through some wires and then through your Bitcoin miner or whatever. Electron separation is really good for solar panels, but bad for
fluorescence. Guys, I want to make perovskites and use lead for Bitcoin.
How does size make the fluorescence happen? Well,
but yeah, okay, so the summary, again, the electron doesn't always just come back from the conduction band and go back down into the, I forget what this is called, I'm just going to call it the insulation band. It doesn't always manage to go back down like that because it could just bump into like another molecule like that is at the surface of the semiconductor. Like it could just interact with air, for example. So it might not always come back in the form of light. It could just be kind of pissed off as heat instead of being released as light again. But I think I'm getting where the nanocrystalline part of this comes from. And I'll say that I don't have too much experience with nanocrystals and nano-sized things. But from the explanations given, I'm guessing that if you make a lot of small nanoparticulate matter, it'll increase the likelihood of the light being released because the high surface area of the nanoparticles interacting with like other nanoparticles that are like kind of surrounding it will make it so that way it's like less likely to jump out into the environment and lose energy to like heat or something.
Well, we're actually making the crystals small enough that the electron doesn't really have that many places to go. And even the distance it can travel across all the crystal, it still feels the influence of that positive charge. So it never really loses coupling with, the hole. And because they're sort of paired and the hole is attracted to the electron and the electron's attracted to the hole and that can't break, what you refer to this as an exciton. So by preventing this exciton from breaking up, you get very good fluorescent.
Yeah, excitons are kind of a very fake term that people just use to kind of keep track of, like, this is a system where the hole is not, or where the electron is not allowed to stray too far from the hole, but it's a little bit of a, it's a little sort of a, it's a fake particle, like it would be referred to as a fake particle, but it's just something that kind of helps keep the books balanced when thinking about this kind of thing. But okay, so that was actually a different theory as to why the light's more likely to be emitted than I thought.
For many people, and I think it's probably the main killer of solar panel yields is this exciton, but I've joined the war on the side of the exciton, you know? Why not? Fuck it. I love light.
And lead.
One slight quirk of perovskites, which is different from other semiconductor sort of nanomaterials, is that the color of the emission, so the band gap of the material and the light that's emitted from there, isn't size dependent. And I don't quite know why that is. Once we're below that threshold where we can retain this exciton, we're always going to be the same emission color. So we should be able to see the same green that's in the paper as long as we get the actual chemicals crushed below a certain sort of size threshold.
I would say that I think so. What is it? It's like the band gap would change in size as the crystal changes in size. I think it's because you end up having so when you do make it larger, you end up, so as the material itself would get larger, you would end up having you just have something on screen. You would end up having the conduction band and insulation band like expand just slightly. It's not noticeable above a certain like size of particle, like this kind of reaches its maximum, but like as you add more things to bond into each other, that molecular orbital diagram eventually like expands, and so you get more orbitals kind of forming further out, and those have different energies and everything is combining with each other. But up to a certain point, you get diminishing returns on size. But at lower sizes, you won't get that. You'll actually get pretty significant changes, and you'll like kind of slowly push these bands closer and closer together until you hit that realm of diminishing returns, in which case you're not really changing all that much. Which you can like sort of just barely start to see here in this little example in the video, where it's like to get from blue to green, that's a 0.5 nanometer increase in particle size. Green to yellow, another 0.5. But then as you get to orange, that's only going to be a 0.4 increase in size. And then from orange to red, a 0.3 increase in nanometer size. Again, it's that kind of diminishing returns of size is starting to take over as the particle gets larger and larger. You're not going to get as much out of increasing the size anymore. And that's orange and red are really close in the spectrum. Same with yellow, while blue and green is pretty far compared, and also green and yellow are pretty far. So it's it kind of you get to see that diminishing returns in effect as the size diminishes, or the size difference between these diminishes as you go.
Materials is that the color of the emission, so the band gap of the material and the light that's emitted from there, isn't size dependent. And I don't quite know why that is. Once we're below that threshold where we can retain this exciton, we're always going to be the same emission color. So we should be able to see the same green that's in the paper as long as we get the actual chemicals crushed below a certain
okay, so he's saying this chemical
threshold.
itself does
That's
not
the end
have
of the
that
theory, but from a practical point of view, we
size
also got to
dependence.
consider that maintaining crystals of this size, getting them to this size and maintaining them there is quite difficult. The material will want to stick together, you know, conglomerate, and it's got all these surface states which also can destroy the exciton. So that's where our oleamine comes in. It sort of what's called passivates the surface, which can do this thing with the charges, so the electrons that piss off don't decay so easily. Also, the particles themselves don't interact as much. So in terms of long-term stability and also fluorescence yield, this oleamine helps a lot. So if we're following the paper, the first step we actually have to do now that we have our perovskite is make oleamine bromide. So we have to make the salt of oleamine, and this just helps to add bromine into the structure.
I'm going to say I don't really know I mean, I kind of know the idea of passivation. I'm not really sure what he just explained there about it, but I guess it kind of helps prevent the nanoparticles from like drifting too far apart. Like I guess maybe it kind of forms an inverse micelle. Maybe I'm not sure.
Or not take the bromine out, because we don't want to destroy the perovskite as we're grinding it. We don't want to break down the material, and the material is a little too easily broken down. So
and then having a little
this
bromine in there
synthesis-
ensures
well,
that like
let's say step 2
it's not gonna
is to
pop off
work
onto
out
the
how to get
organic
this
material,
alliamine bromide.
the salt.
Step 1 really is, how are we grinding these bloody things? Because in the paper they use this plenary mill, which is this really upright, fast, advanced machine.
That sounds like
which
it costs
I absolutely
money.
do not have. I have a rock tumbler. Step 1 is equipment upgrade. Step 2 is alliamine bromide. Then we can do some grinding, and then finally at the end we want to do some color changing. We want to take out the bromides and replace them with iodides, which we may or may not be able to do. But if we can do that, if we can exchange these,
I feel like that
ions,
should
we
be
actually
fairly
change
simple.
the
Although
overall
maybe he might end
material,
up making
which
the
does
particle
change
too
its
big.
emission color. Once again, not making any promises, because I don't even know if we're going to get past step 1. This is Extractions&Ire. I don't know if it's going to work. You don't know if it's going to work. There's a lot of lead.
Lead's gonna make it work.
Too much science. Let's go mix some chemicals.
Lead always makes it
So
work.
to crush our crystals down to nanocrystals, we need a ball mill. The paper we're following uses a plenary ball mill, which is a very fancy ball mill. We don't have that. We have, I mean, it's really a tumbler,
Sort of a ball
right?
mill.
Like it's for polishing of minerals and stuff, but we're using it as a ball mill, using it to grind stuff down. But yes, this won't be appropriate for what we need to do, because we've got to put solvent in and we only have a small amount of material, and this is rubber, so
And it'll
if we
get
start
lost.
putting in
Oh, it'll
toluene
wear.
in here, it's just going to soak into the rubber and just destroy it.
Gross.
And all these metal steel balls are probably going to contaminate our beautiful lead crystals with iron, and that might ruin the fluorescence. So we can't really use this, but
I cannot
I wanna use
believe
that
he's
part.
actually
So
taking
I
like
got a
purity
new
considerations
container.
into
There's probably
account.
a name for it. Anyway, so
For the man that tried to fucking extract chromium, or no, who went and tried to use a stainless steel pot to do a sodium hydroxide like attack on a compound, and was just only then being like, oh yeah, fuck, this is gonna introduce iron and chromium into my sample because it's absolutely eating the pot alive. Now he's finally been like, actually, I don't want contamination anymore.
over here. Here is our ceramic container. I think they're called jars. And I also got some ceramic media. Alumina ceramic bowls.
Holy shit, he's like getting
Look at
actual
these,
stuff.
The fanciest bowls you've ever seen.
Can't believe
Yeah,
this.
actually. The point is they're not actually the fanciest bowls you can get. This is expensive. This was a couple $100 for all the media and this jar, but it's nowhere near the most expensive one. This is not particularly hard. It's reasonably hard, but you can get like stabilized zirconia ones, and that costs twice as much. This was a couple $100, and you're starting to push $1,000. And then you can start doing things like
I am a little interested. Alumina is normally a pretty inert medium, but I am wondering if maybe some of the oxygen from that will end up kind of leaking over and exchanging with the bromine in the compound. There's always a risk of a little bit of ion exchange like that whenever you do some kind of application like this, but I don't know. We'll see.
tungsten carbide, which is very hard and very resistant, but you start to push several $1,000s for this. And you need your jar, your outside container, to be the same hardness as your balls. So you can't just mix and match and get the really fancy
Hard
media
balls.
and then the not so fancy jar. So this is a range of sizes too, which is, I think, better for grinding down to these small particle sizes. So we've got a bit of a mix here. So we'll be using this. It kind of works on the on this tumbler. Obviously put this electrical tape on there to try and make it a bit smoother. I'll put it on and show you what the issue is. Hold on.
Yeah, he splurged on the
It's not
container
too
and the
loud.
balls,
It's a
but
little loud,
not
but it's
not
okay.
upgrading
I mean,
the
it's turning.
actual hardware.
That's a good
stirring
start.
hardware.
But this lid is not. I mean, if we have solvent in here, this lid is just gonna leak solvent everywhere. So
The solution's more tape. I know
work
that's
that out.
exactly
But
what I'm
anyway,
gonna see.
This is probably the entire budget for the video is just in this
Oh yeah, he spent 1.2 Q billion dollars.
new media and stuff, but necessary to do it. Of course, reusable once we clean all the bloody lead out of it. Yeah, this is what we'll be using to crush down crystals into nanocrystals. We'll make it all worthwhile if it glows. That's the hope. Great. So we've got lots of different sized media. One issue is that we got to really mix media with liquid.
I wasn't expecting him to put them all the different sizes all at once. I was kind of more expecting like a stepwise like increase in size. Start with the large balls, then smaller and smaller to get finer and finer powders. I guess if you just put all of them in at once, it might work, but I feel like there's gonna be some weird balancing issue with that, and like maybe the small and large balls are not gonna play nice with each other anymore.
Liquid,
One's gonna
which
crack.
is not going to seal particularly well in this lid, but I've got an ingenious solution, of course, as always. Look, this is slightly tilted so that when this goes here,
That's not a bad idea, I guess.
hopefully
I feel like maybe the
Hopefully all
ceramic
liquid
container is
doesn't
going
leak
to
out the top here. We might have to
itself
tape this
be
closed,
ground
but
down.
Yeah, if it's on this slope, hopefully it doesn't all just drain out. It does mean that this thing hits this little bit, but you know, it's nothing a little electrical tape and Teflon tape can't fix, so it's just jank enough that it might work, you know?
Yeah, this is that Australian shed chemistry that I'm looking for.
Good enough for step 1. Let's bloody get to step 2 and check out this bloody oleamine. Oleamine time. All right, after a very long time, we finally have some oleamine, which we're going to react.
I like his
with
orange
hydrochloric
gloves.
acid
You don't
to
see
make
orange as a
oleamine
compound very,
hydrobromide. Here we
or
go, 70%.
orange is a glove color much.
All right, let's get him out of there. Let's have a look at him and what it smells like. It might smell really bad. I don't know. It is an amine, so I am expecting it to be reasonably stinky. And here it is. It is sort of not really a liquid. It's a bit sludgy. I think, well, actually, I just looked up the melting point, and the melting point's about 26 degrees. So the room temperature is, it's quite cold today, or outside, it's sort of semi-frozen. It's a 70% solution, so in water. It's not particularly fishy, but it is very, not piss smell, but just like the kind of cleaning ammonia smell. The clean kind of, I mean, it just smells like ammonia, really. We've got about 20
not
mils in there,
exactly
another
very
20 mils,
pleasant
and we need to
amines.
react this with hydrobromic acid following the preparation from one of these perovskite papers. Actually, the main perovskite paper, I think, that we're following here, the mechanosynthesis one. There is a slight catch that we made this hydrobromic acid last time, and we know it's not 48%. It's not the maximum concentration the hydrobromic acid can be, and also our oleamine is only 70% in water, whereas in the paper it's kind of a vague 80 to 90%. All this extra water won't affect the ability of the hydrobromic acid to react with the oleamine, but it will affect our ability to collect the end product because the oleamine hydrobromide is quite soluble in water, so if we react it all together and there's heaps of water, even though it will make the salt, it won't crystallize out at the end of it. Instead of
I think you just
ethanol
extract it
as
at
a
that point.
solvent, which is what is used in the paper, we are going to be using isopropanol, which is 100% isopropanol, and then we can boil it a little, and isopropanol has an azeotrope with water, so that means when it boils, it actually carries off a significant amount of water, actually. I think it's the azeotrope's
That's
about
the basic reaction that's taking place.
30% water. So if we put
Just
in
adding
a bit of
hydrogen
extra
bromide across
solvent and then
the
boil
double
off some
bond.
of that solvent, once the reaction is done, it should carry off quite a bit of the water that's kind of residual from all this and hopefully crystallize out our product. That's my vision for this anyway. Hopefully that works. So I think this should be reasonably straightforward, but I don't know. The oleamine already is kind of yellow. It just goes yellow over time. Our reaction has kind of already gone yellow, and I haven't even done anything yet. Only other weird thing about this reaction is, well, we're obviously going to heat it in a flask in this heating mantle. The last time I used this heating mantle, it was smoking because I spilled all this toluene all over it, you know, during the last
burned that off
few
by now,
mantle
haven't you,
reactions.
Tom?
So actually, before I mix any chemicals, let's turn this on and see if it works. Unless it works
It'll just give
perfectly,
you
I think
little
I'm gonna
lung
throw it in the
cancer.
bin because there is quite a lot of power that goes through here, and I don't want it to shock me. And also, look at me, I run a serious business now, so as soon as I spilt the solvent on it, I immediately bought a replacement. So if
wow.
it is starting to
Spent
look
more
like
money.
it will hurt me, which is a distinct possibility if we've corroded some of those wires in there that drive the heating mantle, I am throwing it in landfill, which is what I should do anyway, but I believe in this. You know, the toluene is dried out.
Sounds good, Proto.
Maybe it didn't corrode any of the wires. Maybe this is still fine. It's a resilient little guy.
We're doing organic chemistry right
Doesn't
now
even turn on. See
before
some
we
scorch
get
marks.
into
I'd
the
love to see it. Let's smooth
actual
the
lead
flammables.
work.
It turns on. Okay, good start. It turns on. Let's see if it heats, and not by putting my hand in there. Okay, it is getting warm. It
Bro's
does
obsessed
stir.
with goon. He just wants mine so badly.
Well, that fog is on the outside, right?
Oh, I saw a little bit of smoke. There's definitely some toluene burning there.
Yes. Yeah, it's still steaming. I don't really like that. Yeah, let's use a new one today. Let's use a new one. This obviously has a lot going on in there still.
He'll test and make sure that it doesn't blow up on him
basically
later.
A steam bath now, you know. Let's use the new one.
Cool. Okay. Ooh, look at that transition. It's from goes to that white solid to this kind of like, you know, off yellow oil. Hello, organic compounds doing that. Looks so pretty. A spray of isopropyl. All right, I thought he was going to seriously just pump that to death until he finally got all of his solvent out. I know if you're more of a beer guy, but you can't get over Australia calling wine box wine goon. It's too perfect. Yeah, it does. It's, man, how unfortunate to be Australian and have your regional slang for wine turn into a global slang for cum. Alright, yeah, just doing the simple reaction on screen
Such a dumb setup.
and distilling over slightly.
I just don't want to do it in an open beaker without any sort of column to separate out any boiling of hydrobromic acid, but this is stupid. This is so stupid. Look how it's sitting. That's so stupid.
I'm surprised he didn't just neutralize the hydrobromic acid instead, and then collect it. Like, that would have been easier.
It's gone a bit yellow, but actually very piss colored.
Like, actually, hold on. If he's just trying to get the product here out of the solution, like, I would have probably instead just done the reaction with the hydrobromic acid, and then taken one of the separatory funnel for what he has, and first wash that with a... Well, actually, no, because if you wash it with a bicarbonate solution, then yeah, because his product's going to be soluble in water. Yeah, and then it would be kind of stuck with all the rest of the washings. He said it was soluble in water. That's unusual. Usually this kind of thing does not get more soluble in water if it's this big of an organic group. But I'll let him cook, because I was kind of half paying attention anyways to what he was saying. Any practical uses for what he's doing? I mean, I don't know. He's just hydrobrominating some oleic oleo. What the hell is he working with again? Oleolamine bromide. Oh, that's why it's going to be soluble in water, because he's going to have some extra. There'd end up being protonated base groups on there. You end up with ammonium salts. I really cannot draw it with this mouse. It's actually kind of bad. But you would end up having some of this with like the organic group being here, and then some bromine on the end. Bromine ion. And that'll get washed away with the water, so yeah, no, he couldn't do just a I see why he has to do it this way. Although, I don't know, I feel like if he free-based it, it would probably go back in solution. If he just, like, added some base to this and got rid of the hydrobromic that's on there, like, just suck that away, becomes organic again. Congratulations, you can extract it in an organic solvent rather than all in water, but I don't know. I'm guessing it's probably following the paper, trying to be accurate on that. Yeah, I do need to get, like, a proper drawing thing. I have, like, this little drawing tablet, sort of tablet from, like, when I had a TA in college, or TA in grad school, but it doesn't actually have a screen on it. It's just kind of like like a plug and play, like, draw on this tablet, and it kind of draws at a certain point on the screen, and I didn't want to bother with the technical interface for that. It's kind of not... I don't know. They need more time to test that out and make sure it works. But yeah, like a cheap, like, actual screen drawing tablet would probably be nice. I probably should invest in one of those. It would not be a bad idea.
I don't need a focus to tell that is piss colored. That's piss.
Piss color. So wait, now he's filtering again? Is that what he collected for the distillation? This is a very weird organic synthesis, man.
And we're left with this nice white powder. It's hard to get it completely dry. I've been heating it a little bit under vacuum, but we've certainly got enough here. Even if it's not a great yield, I didn't even bloody work out yield because, you know, this ain't a numbers channel. Who gives a fuck about the numbers? How I avoid bad yield is just by not calculating. Anyway, whatever.
Exactly.
It's a lot
Deny
of
the
powder.
truth.
We don't need very much for each batch of bloody nanocrystals. So now we have this. We can go back to wherever the hell the ball mill is and actually start thinking about making nanocrystals and not this sort of side work. But it's always nice when it comes together. Ooh, drop it immediately. Must have contaminated the outside of the vial somehow, but man, it's slippery. And I was a little worried about it.
And gee, I wonder if
You
your
see
table is
this cold
contaminated.
liquid comes out and you worry when you don't see crystals immediately that I've stuffed something up, but it looks good. So now all I have to do is keep this dry until the next stage, which is very easy to say, but the lab is kind of flooded. Yes, when it rains, it really does get very wet in here. And
Doing chemistry in squalor, dude.
So I'm just fucking standing in this.
This is worse than the usual shed chemistry. Ew.
Don't look at this fucking puddle. This is where you're looking. Hell yeah.
Yeah, at the fucking rotted bench behind
clean.
it.
Don't look at the spiders. All right.
There's not a clean spot in your shed, dude.
Now that's quality. Shit. Fantastic. We have everything we need. We have our bulk perovskite, which we made last time. We have our ceramic media. We have our greasy bottle of surfactant that we need and a little bit of solvent. We're just using toluene, which is not the best solvent from the paper.
Oh, that's what he's using it for. I thought he was using the allyl thing as like some kind of special thing with the cesium-lead-bromide. I mean, I guess there's probably a little bit of something going on there with like being an interface and helping he did explain that like it helps the electron stay in the nanocrystal and like that's how you're gonna get the fluorescence better out of it, but it's also literally just a lubricant for this process so that way the balls in the ball mill don't absolutely just destroy each other. Yeah, no, it wouldn't be able to do anything in that shed. It is, oh god, disgusting.
Have, so I'm still optimistic.
Even worse than the labs that I inspect.
As a solvent. So really, all we have to do now is mix all this together, put it in the grinder, and grind it for a little while, and we'll get some fluorescent nanocrystals. But I gotta say, our bulk perovskite is looking a little worse for wear. The perovskite itself is this bright orange color, which is the cesium-lead-bromide, but the perovskite is not particularly stable, as I keep saying, and wants to break down into cesium-bromide and lead-bromide. And if we look at the two cesium-bromide and lead-bromide, they're both white. So we can see it's kind of returning to a white color or a mix of these orange crystals with areas of white as it breaks down.
Cooked.
So it's looking a little worse for wear. It's been covered in the foil, so it hasn't got a lot of sunlight, but it has been a better part of the year. But now I have to admit something a little embarrassing, because you see this breaking down and you think, maybe, I mean, if you're very intuitive, you might think, hey, what are the chances we're making nanocrystals just by the decomposition of this pure phase? And here I have this UV light. Look at it glow. Look at the green. It's a little hard to see perfectly, but look at the
crystals
green.
already fell apart. He doesn't even
do
all this.
Being, let's take this bulk perovskite, grind it down until it glows, and now our bulk perovskite is just glowing green. Anyway, that's exactly the color we were expecting. That is the perovskite cesium-lead-bromide green.
Now I would call that an energy efficient, solvent-free, environmentally friendly synthesis of cesium-lead-bromide nanocrystals. All you have to add is time. No energy spinning a ball mill, no energy heating it up, no solvents to use dissolving things and then flash boiling it off. Nope. Just give it time and it'll decompose itself.
So this is potentially the simplest and easiest Extraction&Ire video ever, because it has simply worked without us doing anything. I can publish this, right? You know, advanced synthesis of nanocrystals by abandoning your product in a shed for 11 months.
Abandonment chemistry.
Okay, cool. It's pretty bright, but I think we can do brighter, so it would be still good to grind these. But there is a section from the paper that says, alternatively, you don't need to make the bulk perovskite. You can just grind the two bromide salts together with the surfactant, and that will form the perovskite and the nanocrystals.
Mechanochemistry.
Of a little lower quality, but I think it'll be cooler.
Sometimes you can get things to react by literally just mashing them together.
Interesting.
And red fluorescence
is
Oh, that ball's a
Ooh,
little bit gross.
Okay.
That ball has
it
some
will
goon
be
on it.
cooler to
Get
grind
it out of
two
there.
non-fluorescent things together and see it turn fluorescent. Although now the green has to compete with this red of the ceramic. Why is that so red?
And he's gonna somehow get like a
UV torch on things before
purple or
filming these
something.
episodes. Okay, so this is what we're going to do instead. We're going to weigh out small amounts of both of these, small amount of our surfactant, a bit of solvent, grind it together, and see if maybe after an hour or so it forms these fluorescent nanocrystals. Because we have no idea if it's actually working or not if we start with this, because it's already glowing, which once again is just so ridiculous. I said at the beginning of the video that, oh, the bulk perovskite doesn't fluoresce, and here it is fucking fluorescing. Okay.
Well, it's no longer bulk.
The chemistry just wants to be inconvenient, even if it means it's more inconvenient if it works. God damn, chemistry's an enemy. Anyway.
Oh, but this is cool though. Like, you don't often get to see that so-called mechanochemistry of like just actually bashing things together physically, and it causes a reaction. Like, in a sort of like on a molecular level, yes, that is what happens. You're just causing particles to collide into each other, and they react because that's how the energy wants to go. But it's usually things that are dissolved, and they are already like within solution. And so they're already kind of broken apart. This is more just like, well, let's just bash the solid itself together without any kind of medium to, you know, keep them interacting at a molecular level. It's just like, bash them together, they'll interact at the interface.
About 40 minutes. The smell of toluene in the room is quite strong, so hopefully, the solvent hasn't all leaked out.
Probably just evaporated.
Hasn't all dried up.
It's kind of green in there.
I don't know. I'm optimistic that maybe we'll see some green flecks in here, but it does have to compete with the red from the...
Oh my god. That is green.
Am I even allowed to upload an Extractions&Ire video if it works this well? It's just been 30 seconds of silence as I decide, it's perfect.
It's a success.
That's sick. That's so sick. Okay, let's get some out. That's sick. That's so cool. Just another splash of toluene. Just
how to make a medieval peasant's brain explode. It goes in red with this cool torch, and it comes out green with this cool torch. But it doesn't look like much has changed. It's a particularly pleasant color of liquid. I like that. It's like yellow milk.
Yeah. Hell yeah. Not quite as green as... Oh, I suppose there's less suspended in the solvent. Now I've added more solvent. But, I mean, I've got heaps of this material. What if I just scale this up like 10 times? Why don't I add... Yeah, because I've only added a few tens of milligrams. What if I added 10 times the amount and just grinded it a little bit? Won't add 10 times the solvent because it'll leak out, but 10 times the solid. Let's try that out. Okay, so 10 times the amount ends up being just over 500 milligrams of the 2 bromide salts together. Chuck him in there. And this is just over 200 milligrams of the oleum.
Now, how well did you clean the chamber out, Tom? That's another good question.
I'm getting confident now. Just a tiny little splash of solvent again. Yep, all right. And then you could see somewhat on the camera, see where those white...
Okay, so he didn't really clean it out. He just kind of went ahead and reused it.
40 minutes. That seemed like the magic number. Let's get this shit on again.
Doesn't seem to, didn't really seem to want to validate if this just works a second time independently.
All right, so this has been going for another 2 hours or so. It's very yellow in there. I suppose we've made lots of material. It's yellow until we put the UV light on it, and then it is very green. A lot going on. Anyway, that's fantastic. Actually, what is also interesting is this was our previous sample, and you can see all the perovskite has settled out, well, at least most of it, into this nice yellow layer,
look at that. And that's the yellow suspension just right on down. Thanks, gravity.
You see all the green is, even when I have the light very far away from it, all that green fluorescence is coming from that solid down the bottom. We get a little bit of blue from the solvent, maybe from some other contaminant. So if we can wash these solids and maybe make it even more green, well, at least get this green purity a little bit better without this kind of bluiness from the solvent. If we can let this stuff settle out and concentrate it, that's even better. Oh man, I should wait till it's dark and hit this with the UV. Fantastic. All right, let's collect more of this and let's get it
settled out. And then if we've got lots of this, which we definitely have, we can think about trying to change its color with this ion exchange. I'll be honest, I haven't really looked into that much because I didn't.
Oh yeah, that's the other part of the video.
So successfully,
right.
But let's do it. Let's
try
collect all
other
this
little
and
bits
then
of
let's settle
mechanical
out,
chemistry.
and then we can look at ion exchange. Well, it's very yellow though. Why does it go yellow? Why does everything go yellow? Who knows?
Hopefully the yellow is not a bad omen. Yeah, wow, look at all that. Ah, and it's super fluorescent too, even in that dilute toluene solution.
To demonstrate just how bright fluorescence is, because I don't really know what the camera's picking up, and I could just be turning up the brightness on the camera. To compare, I've got some of the most fluorescent household objects you can find. If I turn off the lights and I've got my UV torch, we can see the sort of brightness of these objects. Really, it's the dish soap that's the brightest. Quite green.
No, dish soap was fluorescent.
Post-it note is quite bright. The turmeric
I should try that out.
Pleasant yellow, but is not super bright.
Oh,
These
turmeric's
are some of the
hold on.
Objects.
I have a whole bunch of things I need to go around the house and then fuck with, because I didn't know that dish soap or turmeric were actually fluorescent themselves. That's actually dope as hell. I knew that honey and peanut butter are actually fluorescent as well. If you have the right UV light, you can make them have a small like green glow streak to them. But I actually had no idea about these materials. I have to go do this now after the stream.
Perovskite, and it's potentially brighter than the dish soap. It is extremely green. I mean, it's lighting up the whole room with green. It's crazy. The camera doesn't quite know what to do with all this color. I don't think I've ever seen something as fluorescent as this. I've seen a lot of fluorescent things.
That might be the most.
Let's try out some color changing reactions. We have our perovskite here. It's actually been about 5 days since I made these samples, and I was very worried about decomposition, but they are still very fine. This is the washings we had. It's kind of bluey at the top. I mean, it could just be impurities like the oleamine or something.
Well, I mean, the original unreacted stuff was doing that
bits of perovskite.
too.
I've obviously spilled a drop here, and even the bits that have been out in the light for the last 5 days still glow very brightly. Actually, I washed this media a few times and it's dried out, but I'm never going to get my balls clean, honestly. They're going to be...
Oh no, he has dirty balls.
Forever. But we got very bright green, and this is cesium-lead-bromide. How do we get other colors? Well, we need to change that bromide out for another anion. If we change it out for chloride, we'll shift the band gap of the material towards blue, and we should get a blue fluorescence. And if we change it out for an iodide, to do cesium-lead iodide, it'll shift towards the red, and we'll get this red fluorescence. But
I guess to explain that really quickly, it kind of goes back to these molecular orbital diagrams of like why would changing out the anion change the band gap color. The ions, I guess I could kind of draw this again maybe. If you have, let's see, your basic compound. This is a very, very strong oversimplification of the chemistry, but I'm willing to make that deal. So if you have your bonds kind of like this, you could say that maybe for shits and giggles, we could say that the bromine bonding in is actually like the most optimally matched in energy here. And so when you get these molecular orbital diagrams, you get like this maximum separation. Actually, if it's optimal, then I don't think there's going to be much to wiggle room around this. Again, it's simplified diagrams. But then you have like and I'm just going to simplify everything else as like metal plus, which is an exaggeration of what this compound is, but you get a good energy separation from the bromine because it's well matched in energy. If you did this again instead with like your chlorine, you might have a worse overlap in, or actually if it's going to go blue, it'll probably get, that means it'll get like better. So chlorine gives you a much wider gap in between your orbitals, and this is where the electrons would absorb light to, go up to the next energy level and then release the light to come back down. And so if the larger this gap is, the more blue slash purple your fluorescence will end up being. So if you then could maybe imagine a chlorine, be something a little bit more like this. If you had your iodine, you might have a much smaller band gap. You have something more towards the red. And so that's how you kind of get your different colors going out of it. Each anion bonds better with the cesium-lead mixture than the each one bonds a little bit differently in how good it bonds, and that leads to different band gaps, which leads to different colors.
This is not a salt, you know, it's a solid material with these bromides in the crystal. So we're going to try out a method from 2018. There's quite a few different methods to switch them out. And in my opinion, a lot of these methods, I'm surprised they work at all, because you've got this solid material and you want to switch out the anions without breaking down the overall crystal. And it does damage the crystal. In a lot of these papers show before and after.
Yeah, it's kind of a little fragile.
Synthesis modulation. And a lot of times the crystals do fracture,
ripping out the
smaller in
anions
size,
and
but
putting
the
new
fact
ones
that you're
in.
still able to change out an anion within this solid matrix without completely destroying the crystal is quite impressive. It works.
Well, it also helps that the crystals are so small that you're approaching like, oh, well, there's most of the anions you want to exchange just on the surface of this extremely small crystal. Like, therefore, it's going to exchange without damaging the overall structure very much. And the small ones inside could do a little bit of hot intra-particle exchange to kind of get some of the inner ones out again without damaging things too much. It's reasonable the smaller you get. The larger you get, then that's not happening. You have to break your solid apart.
At all. But we do need the cesium salts, because if we try and use, say, sodium chloride in and mix that in with our cesium-lead-bromide, although
that's going to introduce
bromides
sodium to
are
the
gonna change out
compounds
for
as
the
well.
Chlorides, we're also going to change out some of the cesium for the sodium, and that is such a big change in size between the ions that it will cause the perovskite structure to completely collapse. So we will destroy our material. So if we maintain the cesium levels and put in a different anion, we should be able to change out those anions, or maybe even form a mix of the two anions within the structure, which will still shift the band gap. And so this paper from 2018 uses a sonicator to mix an aqueous solution of the salt and a suspension of the perovskites, or like a colloidal suspension of
very fast vibration, make loud noise, and mixes everything
and I got
on a
my
small
bloody
level.
ultrasonicator here, which is really not meant for science and sounds like you're trying to commune with an alien. It sucks to listen to on the video and in real life. Anyway, let's see if we can get this to work.
He said it's not meant for science. I literally see those in labs.
Bromide, perovskite, entierly, and I'm just going to add some
And people use it for similar things.
It should sink to the bottom.
Ooh, the water's sinking.
Perfect.
Neat.
And here is some cesium chloride I made, I'm going to say 2 years ago, but it may have been 5 years ago or 6 months ago.
I would also say that this is a, the reason why he would do this in a sonicator rather than just kind of put a stir bar in and mix everything is because if you do that, then the stir bar is going to constantly be bashing into these nanocrystals, and that's going to end up just completely ruining the nice crystalline structure that they have, and it'll just kind of break them apart. You want to do something that will agitate the solution, cause the molecules to mix and jump around a lot, but not physically break apart the crystals. And the high frequency vibration will cause everything to move into each other.
Ago or something. So we just have some cesium chloride already here. I made it from hydrochloric acid and cesium carbonate. Let's just add a couple of crystals. We're just winging this because my confidence is high at the moment with the chemistry, and maybe we'll
First mistake.
the light on. We'll see if it changes colors.
Don't believe in the
straight
chemistry.
away. Still looks pretty green to me. So let's get it in the sonicator. I'll get the lid on here. Turn it on. Right.
It's like plutonium rod.
Is high, but let's give it a few minutes. Paper wants it to run for a few minutes, so we'll let this run. Alright, I added more water and a bit more cesium because nothing was happening. It still looks kind of the same green.
Still nothing is happening.
Let's give it a bit more time now.
Oh yeah, shake it. I'm sure that'll help. Alright, so much for a gentle stir.
Still the same. Okay, it's had 10 minutes of sonicating, so I've got to think of something else. Maybe the hexane is an essential part of it. So I've got this cold shellite from the hardware store, which is mostly hexane, so close-ish. Then I'll just put a drop of the toluene suspension with the perovskites in it into this. It's already got the cesium chloride solution at the bottom. That aqueous solution has a couple of
I can see the two
cesium
separate
chloride
layers.
crystals, not quite dissolved yet, but with a stir they'll definitely dissolve. Oh, another drop of lead. I'm really got to decontaminate this place afterwards. But
Lead bench.
okay, now let's see if I can get this in the sonicator and see if this one changes colour. These are two, it's the same colour.
Again, just bash it left and right.
Well, it doesn't look like it either, but I'll keep it going. Okay, I was about to give up on this. I didn't really see that much change over the first 15 minutes of sonicating, so I dumped in quite a bit more cesium chloride into both of these, and I've been sonicating it for the last half an hour. Like, additionally,
One does
to
look
the
like a
first 15
slightly
minutes, I've
more
had
green
45
color.
minutes of sonication.
That's
I was
maybe
just hoping to
progress.
see maybe a subtle color change. Are you ready? Look how blue it is. One of them's gone completely blue.
Nice.
One of them's gone that bluey
Just
green.
wasn't using
Of
enough,
course,
I
compare it to
guess.
the normal green, we got kind of a bluey green. And a full blue one. Hold on, I'm going to get the other camera. Once again, it's too bright. That's crazy. I wasn't expecting
That
this
is
to
very
work.
pretty.
Oh, man.
Nice.
Nothing
You got
is
Mega
ever
Man
gonna
colors in
work
there.
again.
That you got your cyan and you got your blue. It's perfect.
In this lab after the success we've had in this video. This is a terrible omen. All right, that is so sick. Oh, I'm so excited. Let's I need to make some cesium iodide. I don't have any cesium iodide on me, but I have some cesium carbonate and some iodine. So maybe we can cook up a potion that will let us turn this red as well.
He's gonna do some nice, simple,
Now,
basic.
cesium iodide is not a
inorganic
particularly common
chemistry.
reagent. It's not a reagent I have lying around. Actually, well, it's a common material in that it's very often used in radiation detectors. You get these big cesium iodide crystals, and when your gamma radiation goes through, you get scintillation, and you can use that to tell the gamma peaks of your radiation detector. But taking a very expensive, large cesium iodide crystal from a radiation detector and smashing it up just to dissolve it in water is a little too barbaric even for me, and I've done some barbaric stuff over the years. We are going to try and make some cesium iodide. We have some sodium iodide here, but I can't really think of a nice way we can add cesium ions to this sodium iodide and get pure cesium iodide out again without all these sodium ions floating around, which will destroy our perovskite, assumably. Assumably is not a word. In that vein, we'll run with some optimism and just try that anyway. We'll just make up an aqueous solution of sodium iodide and mix that with our perovskite and sonicate it and see if it goes a little red. But trying to make some cesium iodide, I have some cesium carbonate, I have some iodine from, you know, the stockpiles
that's
of
actually not
reagents.
They're gonna use
somewhere.
actual
It's held
iodine?
up
Ew.
better than I thought it
Oh
would.
god.
For being
It held up better,
pretty
but
old. It's just under some water.
it's leaking out of that cap a little
once
bit
again,
there.
Optimistically, I think if we just mix some cesium carbonate with some iodine, reflux it a little, we will form some cesium iodide in solution. Also a bit of other weird chemicals, oxidizers like iodate and, you know, I say you know, but I don't know. I'm assuming you don't know. But if we just boil it, then maybe most of the anions in there will be
I'm
iodide,
not exactly
which is
sure
good,
how his
because I don't really
idea
know
is going
what
to balance,
iodate is
but
gonna do
good
to
for
our
him for
perovskite.
trying.
Might destroy it, might do nothing. So a little bit of experimenting here, you know, just doing some potion making. Why not? So cesium carbonate and a little bit of water with some iodine. Let's see if we can reflux that. Well, just
I
boil
guess
it.
that sort of
We've got nice
produces
and clear.
some
We've got
I
some
minus
demineralized water.
in
Coles
solution because
simply
it forms like
demineralized water, product
some
of Australia.
hydriodic
Look at us go.
acid. I guess
And
that's
they
sort of what
say
happens.
Australian manufacturing is dead. Look at us go. Demineralizing our own water. That's sovereign capability if I've ever seen stuff. Yeah, look at us. Hell yeah. We're independent. All right, fuck it. Let's do some chemistry.
Yeah, I guess that's his idea. He'll end up forming a little bit of the hydriodic acid in solution by adding iodine to water, and that will combine to form the cesium iodide, and then the carbonate will off gas as off gas as hydrogen carbonate, which actually would then be water and carbon dioxide again, with a little bit of heating. So, interesting. That's certainly not the approach I would have expected, but I guess that works. Alright, then he's going to compare doing the adding sodium and seeing how that ruins the perovskite versus using cesium iodide and seeing if that keeps it working. Oh, one of them's getting a weird color. I think that one's that's the sodium one. That one's fucking up. As expected. And then the other one's also screwing up. Ruh-roh.
After 10 minutes of sonication, both of these solutions, this is the one with the sodium ions and the one with the cesium iodide, well, hopeful
sodium one still
iodide.
looks interesting.
Yeah, both of them are a bit messed up. They've gone red. Maybe there's a hint of red fluorescence. Actually, I mean, look at that. That's glowing red. That sort of did work. What? Yeah, that one didn't work. So maybe the sodium iodide isn't as destructive as I thought. It's obviously not as bright. So it is getting
it's
wrecked
still pretty
in there,
destructive.
but not as wrecked as these ones because it just looks like it's a fine white powder. It's actually all left the organic layer altogether. Probably precipitated out lead iodide or something. But that's a promising sign. I wonder if we can sort of combine these two, like have some cesium iodide and some
make your
sodium
cesium iodide a
and
little
see if we can
better.
get this red fluorescence a
Maybe.
little brighter. We've obviously exchanged out some of the anions for the iodide, but we've just also kind of destroyed the framework a little, which is why it's so dull. That's my guess.
Okay, I thought about this a little bit longer, and my cesium iodide solution, well, my supposed cesium iodide solution, the one that caused really quite significant decomposition in the perovskite, it was extremely basic, you know, when I checked the pH, and it's really, you know,
it should not be like
force
that.
chemistry to work. That definitely won't work.
Especially when it's supposed to be kind of acidic to start off with.
I was boiling it and trying to reduce some of the iodate that would have formed, but yeah, I don't know, it was getting really basic, so I tried to adjust the pH more neutral with some sulfuric acid, but then the iodate reacts with the iodide to make iodine. You see that as that yellow brown. So I was kind of going in circles for a long while. I dried out the solution, tried to decompose the iodate that way. This sort of vibe-based chemistry sometimes doesn't work because you can't just have an idea of how chemistry should work and it does it. But I eventually added some sodium thiosulfate as a reducing agent, which will reduce the iodine down to iodide and still give us a reasonably neutral pH. The downside, of course, is that we added some sodium, which I was trying to avoid.
Yes,
but
too bad you don't have
couldn't really
cesium
find a
thiosulfate.
good reducing agent that I have on hand that would do that well. So we have this solution now. It's absolutely chocked filled.
I mean,
with
carrots are a
cesium
reducing
ions,
agent. You
a
could do
little bit
that,
of
but that probably
sodium
also
and
introduces
iodide.
sodium.
The pH is neutral. So let's give it another shot in the sonicator with this solution. I mean, it's a little bit cloudy because the thiosulfate does produce some sulfur, which is kind of colloidal sulfur. So actually, we'll check if that glows at all.
Didn't feel like
blue hue to
filtering that out.
Trying to chase this red color here. Let's get everything together and chuck it in the sonicator.
Now you're gonna
one
add
more time.
sulfur
I'm gonna
into
start
your
panning the, UV
perovskite?
light over this desk because then you can see all the contamination. It's like bringing a UV light to a hotel room and
Ew. Instead of goon all
feeling
over the desk, it's
disgusted,
lead.
but, you know, in this case, I'm bloody spilling lead everywhere rather than spilling. You know what I've always said? I'd rather be shooting lead than firing blanks. You know what I mean? I can see that on a bumper sticker, you know?
Why not both?
I'd rather be firing
Lead's not good
than
for your
shooting
reproductive
blanks.
system either.
Fuck. All right. Let's get this fucking chemistry on it. It's maybe a slightly different green, like a deeper green, but yeah, it's definitely decomposing once again. And it's definitely not red. So the best success we've had so far is still just with the sodium iodide, which makes this red one, which has a faint red glow. So why don't we just try...
I'm guessing the
something
sodium
along
iodide
those
one's
lines
working.
again. Forget this weird cesium solution. Let's just...
I'm guessing the sodium iodide one is working best, probably just because it's not some fucked up amalgamation of random shit from his shed, and it's just like, hi, I bought sodium iodide. It's me, your friend, sodium iodide, purchased from a manufacturer.
Flood it with sodium iodide. Let's flood it with sodium iodide. All right, this is cesium bromide and sodium iodide. It's about 50-50 just by volume. It's once again just
so he's kind of trying to trick things a little bit.
Ions already in solution, so maybe we won't pull so many cesium ions out of our framework. So if you can replace some of the bromides in our structure with iodides, we should
See,
still
but that's also going to make the bromine replacement less efficient because there's also bromine in the solution too.
And it's changed color straight away. Oh,
Oh wow, that one was
Didn't
fast.
need a sonic gator.
Oh, look at that, and it's going red and orange right before your
That was
eyes.
quick.
God
Oh
damn.
man, I have to decontaminate this whole area, but damn is that pretty. Once again, they're not as bright, but god damn is that red. Wow, that was quick. So we managed to get some color tuning, but the stability of these products isn't that great. I mean, I made these ones about 5 days ago now, these blue ones, and they've been in contact with the water, so I think they're more prone to decomposition. There's still some blue, but it's nowhere near as bright. And these orange ones, we never really got super bright. In fact, maybe the first attempt was the best one. Anyway, the final thing I want to try out with these is my stretch goal of making
Hey, Grim, welcome.
films out of them, because obviously we can see that they start to decompose.
You talking about shooting lead instead of rope? You're acting freaky even without me. True, you know it. I mean, man was getting. Just take a look at all the lead that's on the desk, man.
Rather
Just
than
the spots
spilling.
everywhere.
You know what I've
It's
always
gross.
said? I'd rather be shooting.
But yeah, welcome. We're getting towards the end of this video, though I do have something else to react to after this, so
We can dry them
Fun's
out,
not
as,
over.
as we've seen from the contamination on the bench, and they
oh yeah, so actually
try
okay.
out with these is my
There we
stretch goal of making some films out of them, because obviously we can see that they start to decompose, and we haven't had a lot of decomposition in about a week or so since we've had this lead bromide one, but over
Something you
time
made that's
and
actually
exposure
fairly
to
stable?
air and light, it's going to break them down, and we can dry them out as we've seen from the contamination on the bench, and they do stay glowing, you know, when they're not in solution or in suspension, but that will fade. However, how do we get them into a film? Well, if we just mix them with a polymer and then set the polymer, then we should have something that glows very nicely. And there's some papers that do this in a PMMA film, a polymethyl methacrylate powder, which sounds a bit fancy, but that's just the name for acrylic, and you can get acrylic powder
resin
very
cast
cheap
these
for use
nanoparticles.
in,
That's
like,
actually a
fake nails
pretty
and-
good
and
idea.
nail art. Now, you might have just had the idea of, wow, you can make really cool glow-in-the-dark nails with this. You could have nails that
With lead. With lead.
glow under the UV light. No, you've forgotten about the lead in this. Your brain craves the lead. Got that idea because you
Gen
want
X
to
nails.
be exposed to lead. But that's a bad idea. No rave is worth lead exposure. So we're not going to be painting our nails with this
TikTok
stuff,
would argue
but
otherwise,
I
Tom.
want to dissolve up some acrylic. It should dissolve in the toluene, which our stuff is suspended in, and then we can flatten it out, let it dry. The polymer should be there, and then we want to pull off that
Exactly,
polymer and
yummy
have this
paint
nice
chips. They're
flexible
delicious. His
bit of film
bench probably
that
tastes
glows
like
really brightly. We
Doritos,
obviously
you
have to
know.
peel off that
So
film,
much
so
good-
I've just got
good
this
stuff on
Teflon
there.
beaker. Hopefully we can let the solution dry.
Only a little
on
bit of
here,
lead.
and then the Teflon should be non-stick enough to peel off the film. That's my goal here. So let's do a dry run, as in a run without any lead in it, and see if we can make an acrylic film and get it off the beaker before we start mixing the lead in there.
Good old
Here's some
Teflon.
toluene, just got
May have
some
to
warm
endure a
water.
little bit of fluorinated
Warm with the warm
microplastic,
water.
but it's
How much of
completely
this acrylic
nonstick.
powder we can dissolve in there. That's an acrylic smell.
Okay. Have you actually? That's a good question. Hey, Grim, have you ever actually tasted Play-Doh? Because maybe me and my mother did when I was younger, and we were playing around with Play-Doh because I was a little kid, and it kind of had this nice salty taste to it. We didn't like eat it, but we did kind of lick it, and it was pleasant. Yes, ironically. All right. Or Play-Doh liquors. Hell yeah.
Looks like it dissolved.
So now we can just, graduate to lead-coated
It's getting
Play-Doh.
thicker. All right, that looks about all that will dissolve. So let's pipette a small amount onto our.
You
nice
ate the whole
Teflon
dang dough.
substrate.
You must have had some
Chocolate
colorful
Ecarus
shit.
substrate.
Yep, non-fluorescent. It's acrylic. Let it dry.
Yeah, it needs to dry a bit longer. Got potential though. It has potential.
Get impatient. Use hairdryer.
Oh yeah.
Minty green logs. Epic. Oh, Minto reference. Nice. Any stupid jokes.
yeah.
Anyways. Look at that.
Oh yeah. That's it. Perfect. No color on the UV. That's it's just acrylic. Don't know what the hell is on those tweezers. It's not lead though, for once. All right, let's add the lead.
There's something on every single thing that you own, Tom. You haven't cleaned this lab in years. Oh, you missed. Maybe I'll rewind to it later, Grim. But you missed his like disgusting post-rainstorm use of his shed. It was just the absolute most squalorant location I've ever seen somebody try to do work in.
Alright, let's try this out. Yeah.
Look at that. Oh, that peels off so damn well. That's bloody perfect.
Oh, are you seeing this shit?
And this is why all those material science people love researching the nanocrystals.
Does it glow? Yeah.
Forbidden deviled
I'm
egg.
thinking it
True.
glows.
It's more like egg film, egg sheet. Oh, look at that.
Very
A
yellow.
way to make a green
Before it
light,
was
sorta.
Completely clear, and then it turned green. But I'll give it a pass for being yellow because look at this thing. Just a green torch now.
Spongy McMuffin egg. Yeah, actually,
This
it's like
project
that.
has been
Liquid
so
egg.
successful that we actually finished before it's spring. So before the birds came back and tried to build their nest again. Well, actually, the nest is already there, but before they came back and started laying more eggs. So no birds this episode because of success. So I hope
And definitely not
whatever
because of
you
lead
do
fumes.
goes as well as this, whether it be fire and lead or shooting blanks. You know, I hope it all goes well for you. It's time to decontaminate and get a lead blood test. Cool.
Oh, but yeah, let me show you, Grim, what he was working with at the beginning of the video. Yeah, this...
Actually,
He was showing off
thinking
his
about
starting
making
material.
nanocrystals and not this sort of side
Or-
work, but
Well, yeah,
always
one
nice
of
when
his
it comes-
materials, and
The lab is kind of flooded. Yes, when
Ugh.
it rains, it really does get very wet in here, and it really did rain recently.
just
So I'm
awful.
just fucking standing in this health and safety nightmare. Anyway.
And then
Don't
his
look at that. Don't
fucking
look at this
corroded ass
fucking
bench to
puddle. Don't-
boot. It's just,
this-
oh, it's so
This
gross.
is where
Like,
you're looking.
he used to work in a professional setting. How can he let himself go like this? But anyways, well, that's cool as hell, though. If it didn't involve so much lead, and I would love to try and make some of this at home someday, but maybe sometime. You experienced a flood damage since your dad's basement flooded? Yeah, I mean, I used to also have, like, my parents' basement would flood too when I was growing up, but thankfully it was a apartment basement, so it wasn't ours to fix. It was still quite irritating, though, with lots of detritus and animal feces washing up. But this is an outside shed. He has sort of some excuse, but then also the fact that he's just doing it here, it's like, ugh, gross. Caking his Batman comics to the wall. It's permanent foundation now. Well, at least you know you have a hero standing up for your home. So that's kind of good, even though I'm sure that the loss of Batman comics was gratefully mourned. But anyways, I will do have one more video to react to. I found the other day, it's been in my watch later for a little bit, making the world's strongest nitric acid. I'm not entirely too sure what we're doing going past red fuming nitric acid, but I gotta say, I am interested. So I do want to actually spend some time, sit down, react to this for a little bit. I do need to use the restroom before I do that, though. So let me quickly pull up some music for y'all and change this over to the BRB screen. Unfortunately, I did not put the I gotta take a piss art on here. I could maybe do that, actually. I shouldn't bother. I should just get things rolling. But yes, I will be right back after I get you some music to listen to. Let's pull up that stream background playlist, which I did mention earlier, but in case you've ever been wondering what I have been playing in the background, I do actually have a stream background playlist on my channel / in the description. So if you ever want to check that out, go ahead. But anyways, yes, I will be right back, and we can then do some more fun reacting stuff. I'm back. I was talking about actually as the stream was beginning, so one of the unfortunate things that is actually causing, as like a low priority secondary effect of like why there's just been fewer chemistry react streams around is like, remember the USCSB videos, like the industrial accident investigators of the US government? Well, guess who was subject to Doge cuts and other things, so they might not be around for a while, and if they can't find some alternative means of securing funding. So we're kind of down to just watching for Australian man and Canadian man to do some kind of chemistry upload, unless I find more channels that upload 30+ minute chemistry videos. It's gonna be a little bit of a dry spell for that for us here on the channel. But thankfully, as the second video I did have today was this video on making the world's strongest nitric acid. And I gotta say, I am curious. I'm a little bit baited into what the hell they're talking about, because I know you can make some really strong nitric acid with the red fuming nitric acid stuff. Infamously, red fuming nitric acid will eat through your standard lab gloves of latex and nitrile. And that's like 75% plus nitric acid, and it looks like this guy's going for something higher than like 90 and 99%, so it'll be pretty cool. Chemistry adjacent games could be potential Thursday stream material. Can't think of any at the moment. Yeah, no, it's kind of difficult. Like any chemistry type games I try to think of, like the only chemistry that games that are like kind of faithful I can think of is basically just like the Minecraft chemistry educational edition, which I don't know, could be fun to check out at some point. But and like I think there is some other like usually the other chemistry games that are kind of dedicated to accuracy are like drug making fantasies, and it's like, okay, guys, come on. I have some standards. But yeah, it's a little bit of a shame. There isn't too much chemistry related content in that sense. I mean, there's other, like, I'm sure there's other like potion making and selling games and stuff like that, but I need to stay within the realm of the real for me to express my chemistry knowledge and make something cool out of that. It's difficult, but I mean, if anybody ever catches word of chemistry related games, then please send it my way. I would love to actually check stuff out like that. I think that would be really cool. But yeah, hey, speaking of, we got so there were not very many explosions and fire in the last vid from the guy who normally goes by Explosions and Fire on his main channel. So let's watch some explosions and fire on this random channel. Ah, yes. That's how you know they're insane. They're not wearing gloves while we're doing any of this.
Welcome to Amateur Chemistry. So, nitric acid.
Is there any way to make the captions smaller? I kind of would like them with the thick accent going on, but these are extremely large captions. Let's see here. Annotated audio, subtitles, options. There we go. Okay. Character edge style. What the hell is half of this? I don't really need to customize my captions that much. I just need to make sure that they're not huge. Font opacity, window color, font size. There it is. Okay. Blind. That's a really weird way of him stacking his captions. All right, whatever. We'll go with it.
I am sure most of you know just how useful and important this chemical is, and I am not talking on an industrial level, but even in the amateur chemistry lab. Nitric acid is what allows chemists to perform thousands of amazing reactions, from the
yeah, it is really awful paragraph breaking.
Nitrate salts or refining precious metals.
And it's not
some
YouTube
things.
Automatically doing this. It's this
there
guy.
Is no doubt that every chemist needs this stuff in their lab, and what's quite sad is that
maybe he was
it's
meant for a certain
impossible to
size.
That,
if
however,
I go down
doesn't
smaller.
Stop people from just making nitric acid themselves, often from seemingly unrelated things, a prime example of which are some of my older videos where I made nitric acid from fertilizer or even wood. There are hundreds of other methods documented by many amazing chemists here on YouTube, and if all you want is some concentrated nitric acid for experiments, they are all fine. If you are like me, however, and got bored of watching the same thing be done over and over, I have good news for you, since for a while I've been wondering what 100% nitric acid is like. You see, the thing with nitric acid is that its properties heavily depend on its concentration, and while the dilute stuff isn't really dangerous,
I mean, it's still kind of dangerous, but
let's just say
yeah.
scary, and even professional chemists often refuse to work with this deadly component of rocket fuel. That's exactly why I decided to make it, and since pretty much nobody made and tested pure anhydrous nitric acid on YouTube before, I was really eager to see.
Yeah, that's a real energetic mix. That's an aggressive oxidizer.
This seemingly well-known reagent. Now,
this is gonna be interesting.
Before I start putting my safety gear to the test, I have to warn you about just how deadly and dangerous the stuff you are about to see is. Concentrated nitric acid is not only really toxic, but a stupendously powerful oxidizer capable of easily setting most lab gloves on fire while generating copious amounts of the incredibly deadly nitrogen dioxide gas, which when entering your lungs basically turns them into mush.
If the nitric acid also touches your hands, it'll turn it very crusty and orange for a long time, as it absolutely eats your skin.
Through years of chemistry experience, I've built up enough safety precautions to deal with such deadly chemicals.
You will look like a carrot for a while.
This video is not a tutorial and is for educational/demonstration purposes only. With this out of the way, I can start whipping up some real strong acid, and to truly show you what it means to have pure nitric acid, I figured that I would first start small and make some weaker stuff you might normally find in a lab. The first nitric acid that many chemists make is what I call poor man's nitric acid, and as this name suggests, it's quite dilute and kind of dirty.
It is what it is, ain't that the fucking truth?
Nitric acid in many
this is what you use at home when you don't have access to professional ingredients.
The ingredients that I will need are actually the same ones I will use for making all the other quote-unquote levels.
Alright guy, really showing off with your fucking turntable for your chemicals.
Mixing them is the best and cheapest way to obtain various
oh my god, YouTuber ass setup.
And for my poor man's stuff, I wanted to use 90 grams of concentrated sulfuric acid diluted with roughly
5 minutes experience with text formatting
water.
apparently.
Will really ease the synthesis.
You can't hold it against scientists. They don't really care about aesthetics too much. No, you can't absolutely. It's pretty bad.
Acid is quite necessary as it generates a bunch of heat when mixed with water.
Anyways, yeah, so we're diluting sulfuric acid, and he's probably going to add a nitrate salt to it.
100 grams of potassium nitrate, which
very simple way. Sulfuric acid's more acidic than nitric, causes that reaction, and you get your nitric acid.
And a salt called potassium bisulfate.
It's not a perfect conversion because it's not super much stronger, but it will get you, it'll get you to it is what it is quality.
From many nitrate salts. After adding all the potassium nitrate, I now wanted to forcefully drive this reaction to completion, for which I got everything onto a hot plate and turned on the heating. This quickly made all the undissolved nitrate go into solution, and now with the reaction complete, I wanted to remove some of the potassium bisulfate byproduct, for which I put the beaker into a fridge. This made a part of the bisulfate crash out as these small crystals, which I was able to easily remove by vacuum filtration, leaving me with some clear, dilute nitric acid. Now, since there is still a good bit of potassium bisulfate in it, I can't really calculate my yield or its concentration. However, from my experience, the yield should be around 90%, and based on the amount of water that I use,
yes, from my vibes and the way I've measured things before.
Solution. As you can see, this acid is far from perfect, being only visually clean and incredibly weak. I mean, it doesn't even light my gloves on fire, so I think that for the next batch I can do a little better.
Yeah, my PP is actually working. This isn't strong
what
enough.
You most commonly find in a real lab, since it is both concentrated and safe enough to be used for pretty much every reaction requiring
Looks a little bit more concentrated than what we typically find.
Azeotropic nitric acid, and I'll explain what that means in just a minute. Its concentration is usually around 68%, and since it has almost 3 times more acid than the poor man's stuff, you can probably guess that it's way more fun. Making it is also strangely straightforward, however, as with every new level of nitric acid, it requires quite a bit more glassware and equipment, which is kind of similar to how you would unlock a new chapter in a game. If you think about it, chemistry is kind of like a game where you actually die when you screw up, and each new level of danger requires more
die in the game, you die in real life. The game is real life.
To unlock more concentrated nitric acid, I began by choosing this flask as my reaction vessel. This time, I added the potassium nitrate first and used 330 grams. In terms of sulfuric acid, I chilled 340 grams of it in a freezer and had to dilute it with around 100 milliliters of distilled water.
Exactly. Press IDDQ and you'll just get your, infinite concentration.
Initially well below zero, the resulting solution was nearly boiling. I let it sit for a few hours to cool down a little and then just dumped it all into the flask from before. I then assembled it into this simple distillation apparatus, which will allow me to remove nitric acid from the flask as it forms, greatly increasing its purity and concentration. After just a while of heating, the mixture began taking on an orange-brown color, and this signals that nitric acid is being produced, since when it's heated and concentrated enough, it easily breaks down into nitrogen dioxide gas, which is brown. This spicy air quickly filled the whole apparatus, and it's one of the main reasons why I am doing all this in a fume since breathing this stuff in equals permanent lung damage.
Soon.
Anyway, as the flask warmed up, all the potassium nitrate dissolved and the resulting solution began to boil. Its vapors quickly traveled to the condenser, where they turned back into a liquid which then dripped into a receiving flask. Now, this liquid is actually a mixture of nitric acid and water and boils at 121
If he doesn't explain azeotropes well, I'll have you covered.
Above water's boiling point and a whopping 38 degrees above nitric acid's boiling point. It contains roughly 68% nitric acid by weight and is the so-called azeotrope I talked about earlier. Its formation makes obtaining 68% nitric acid very convenient, but it also means that you can't really obtain any stronger stuff by conventional distillation. That's why I will have to use some special tricks to go up to 100.
So it seems like he's not really explaining it very well, but so when we have the concept of an azeotrope is basically the concept that when you have two liquids together in some combination, they may actually not separate by distillation. So normally you would be able to distill two liquids by their boiling point. If water boils at 100 degrees Celsius and you have some other compound like it's hard to come up with a good example that does mix but also doesn't form an azeotrope. Let's say like acetone. I'm not sure if this is a great example or not, but acetone, which boils at somewhere around like 60, 70-ish degrees Celsius, if my memory serves me correctly. Boiling up that mixture up to 60 degrees, your acetone would come off as vapors. You'd be left with pure water in your starting flask, and acetone in your receiving flask at the end. The idea of an azeotrope is that, well, actually you have two substances that when mixed, like nitric acid and water, they actually combine there is a certain like minimum of temperature of boiling point versus their percentage combination, and so that leads to the two components being inseparable, or they have a new kind of combined boiling point, and they will come over at whatever this concentration of nitric acid and water is. In this case, it would be 68%. It boils as if it was one liquid. They do not separate by distillation. You're just basically actually taking over a nitric acid water mixture of 68% in the gas. That is also the 68% in the liquid as well. And this happens because if you imagine having a higher concentration of nitric acid like this, you start off with something at a high boiling point, but as more of that nitric acid kind of boils off, the remaining solution ends up just turning into this lower minimum. Same thing if you start with something that's mostly water, you boil off more of the water, you end up, again, going towards this minimum. Actually, wouldn't be boiling off the water because the nitric acid would be coming over first, but you basically you end up having like this minimum in boiling temperature that everything kind of just coalesces down to, because like, well, actually it wants to be at this percentage mixture, and so it'll kind of just start acting as the one boiling point, the one temperature, just one kind of mixture that is kind of, that can't really be separated by just boiling alone. It's the same reason why ethanol, the most you can actually distill ethanol up to is 96%. To actually get the remaining 4% of water out of there, you would need to use something like molecular sieves or a drying agent to suck the water out of solution. So you could not get a distilled spirit past 96% ethanol. Fun facts.
% nitric acid, and to finish preparing this one, I just waited for the distillation to complete, and when no more liquid was coming over, I turned off the heating and collected my product. I ended up with quite a bit of it, which was really cool, and since this time it's just a mixture of nitric acid and water, I could actually test my product's concentration. This can be done by measuring its density and using this handy-dandy online chart, which told me that the acid I made wasn't quite the 68% I hoped for, but instead sat around 60%, which is probably due to me using a little too much water and not redistilling it. It should still be alright, however, and its reactivity is pretty much exactly that of the azeotrope, meaning that it still can't set lab gloves on fire, but starts to make them burn faster. This nicely
it's an
showcases
oxidizer.
how water has this kind of a dampening effect on nitric acid, and its removal really allows this acid's chemical aggression to shine. Speaking of chemical aggression, I think it's time to move on into the more uncharted territory of nitric acid concentration.
Look at that, even safely squirting water onto it instead of like just dumping a whole bucket over it.
This will result in something called red fuming nitric acid, or RFNA for short, and much like the azeotrope, I will explain this name in a minute.
I think it kind of is a little self-explanatory there. It's red, it's fuming, and it's nitric acid.
And as expected, requires quite a bit of preparation to make. This basically means that I have to take extra care in excluding all the water from the reaction, and the best place to start is by drying the potassium nitrate. This seemingly dry powder has quite a bit of water in it, and to get rid of it I got some into a baking tray and roasted the hell out of it using my trusty oven. This made it visibly drier, not forming any lumps, which was very good, and to start making extra spicy nitric acid, I got 400 grams of the dry potassium nitrate into a flask. I then followed this up with 420 grams of chilled sulfuric acid and assembled the flask into a simple distillation setup much like before. This time,
it seems maybe a little bit excessive, because the sulfuric acid is already pretty good. Well, one, it has some water in there, but then it's also a very good desiccant on its own. It would probably have extracted the remaining water out of the the potassium nitrate powder without the drying. But yeah, you know, being extra thorough.
I could really tell that I was working with some strong nitric acid, since the amount of nitrogen dioxide generated was quite crazy. There were also these very cool rings of white fumes coming out of the apparatus, and this is the fuming part of red fuming nitric acid, since at such high concentrations
it's like the smoking caterpillar.
It likes to attack moisture from the air, producing these incredibly corrosive acid fumes.
They just let go out into the lab, it's fine.
Seemed to go way faster than before, probably because of pure nitric acid's low boiling point, and it didn't take long for the vapors to stop coming over. In the end, I was left with a good bit of some clear apple juice looking liquid, which is pretty much pure nitric acid. It still isn't completely pure though, since there is quite a bit of nitrogen dioxide dissolved in it, giving it this reddish tint, which solves the remaining mystery of its name.
You're never gonna get rid of that.
To make the final level of nitric acid in this video, I will have to figure out how to remove the nitrogen
so here's
dioxide
we get to the
as
weird
well as
stuff.
all traces of water. However, for now, I don't need to care about that. To finish preparing the RFNA, I measured its concentration using the exact same method as before, and it came out to be around 99%, which was quite
just don't handle it. No gloves on, fuck it. It's gonna burn the gloves anyways.
Since this acid is virtually dry, and you can really tell because of how it reacts with my gloves. This spontaneous combustion is
I
why
love that
avoid
demonstration.
using gloves when handling pure nitric acid throughout this video, and it's so corrosive that virtually the only way of storing it is in a glass bottle with a Teflon tape sealed lid. You might notice that I have quite a bit more of this acid than what I just made, and that's because I actually had some left over from a long time ago and just decided to combine the two, especially since I will use a great chunk of this stuff to make the anhydrous nitric acid.
Hey,
Speaking
no
of
water
anhydrous
nitric acid.
acid,
Oh boy.
I was really curious if getting that...
That's kind of frightening that it's not colored at all for me, because I just associate high concentration nitric acid with, like, yeah, it's putting off nitrogen dioxide because, like, there's just the nitric acid does not want to be stable, it doesn't want to move up. This implies that actually no, nitric acid itself is stable. It's just a little bit of water that catalyzes it to turn into nitrogen dioxide coming off. That's scary to me. I don't this looks scary.
Last percent of purity was going to make it that much angrier, and I suppose that there is only one way to find out. The tricky thing about making anhydrous nitric acid is that there are pretty much no sources on it anywhere, and at this point in the project I was feeling kind of unsure.
How do you
if
keep
I
all
would
the water
succeed.
from, like, the world out?
I could use something like the incredibly expensive phosphorus pentoxide to chemically react all the water away. However, I would then have to distill the dry nitric acid off, and this would mean losing a ton of it to decomposition. For some time, I kind of lost hope of obtaining completely pure nitric acid, but then one day I stumbled upon this US patent from 1975 about doing just that. I mean,
and it's not military grade?
True,
This is fun.
claiming to achieve anhydrous nitric acid using really simple chemistry, so logically I was quite eager to try it out. First, it called for using this cool piece of glassware called a separatory funnel, which I was to fill with some fuming nitric acid.
It's just a big piece of glass you could shake around.
Since I didn't really know if this whole thing would work, and I prefer not to work with
you could funnel
too much
stuff out.
rocket fuel grade nitric acid at a time. To remove all water from nitric acid, the patent called for the addition of roughly half its volume in concentrated sulfuric acid. The two acids easily combine, and since sulfuric acid really loves water, it basically steals it from everything, including nitric acid.
Oh
now,
wow, you can see the color go away too over time.
Is how you go about separating the anhydrous nitric acid from this corrosive mixture, since, as I said, distillation isn't really an option. You see, it turns out that the very common lab solvent dichloromethane can actually dissolve nitric acid while leaving sulfuric acid untouched, and indeed, upon adding 50
Interesting. I didn't think that it was actually
into the funnel,
those two would actually miss, but I guess they are kind of both
nitric acid into it, I aggressively
non-polar,
the funnel
or they
and
both
then
are kind of
waited
polar,
for
so
the layers to separate again. I drained off the lower sulfuric acid one and got my precious anhydrous nitric acid solution into a flask. To squeeze out more nitric acid from the remaining mixture, I again washed it with 50 ml of dichloromethane and combined the resulting extract with the stuff in the flask.
Well, it's kind of getting red again, so
it should contain pretty much all the nitric acid I started with in a completely anhydrous state, and to get rid of the dichloromethane, I just have to boil it out. First, however, I wanted to remove this weird cloudiness from the solution, which probably came from some suspended sulfuric acid droplets. I tried to use anhydrous sodium sulfate.
Yeah, see, the problem is this is just kind of making the...
It's like the only thing not to react with.
This is just making the whole solution more complicated.
After a few hours, all the cloudiness disappeared, which was very nice. And to start removing the dichloromethane, I poured everything into a different flask. I then set it up for yet another distillation, this time using a hot water bath to warm my nitric acid ever so gently. Well, maybe not so gently, since right after adding the hot water, a bunch of nitrogen dioxide appeared, and the dichloromethane started vigorously boiling since it has a boiling point.
Yeah, that's kind of 60 degrees Celsius over what you needed.
Even though this whole thing looked quite chaotic, it really wasn't that bad, since the nitric acid decomposed just a bit and didn't even begin to boil. After a few minutes, most of the nitrogen dioxide disappeared, which meant that my acid was no longer decomposing and the dichloromethane was boiling away quite steadily. When all of it was gone, nitrogen dioxide started to appear again, which was a good indicator to stop the distillation. In the end, it left me with this rather small amount of anhydrous nitric acid, which wasn't quite the 50 milliliters I started with, and if I were to do this again, I would definitely use some more dichloromethane. Anyway, now that I have removed all the water from my nitric acid, I have to do just one final thing to make the ultimate forbidden water, and that is to get rid of all the dissolved nitrogen dioxide. There are a few ways to do this, but the best one in my case is using this really old ozone generator,
that's interesting.
which, while originally
because
meant for food
actually
and
the
will now
nitrogen dioxide is like basically just the a reduced form of nitric acid. So if you just see, if you just have nitrogen dioxide look something like this. Oh, this is kind of a crappy diagram, but you'll have to deal with it. I'll try to make this look a little bit better for me. If you just have your nitrogen dioxide that's dissolved in there and you react it with some highly reactive ozone, then that will basically just allow you to actually go ahead and form this into nitrogen trioxide again, and that's only just a step away from picking up a random hydrogen from like the last little bits of water left over and turning right on into turning right up back on into nitric acid. We just plus H2 from somewhere, or plus a proton from somewhere, will get you right back up to nitric acid. Yeah, no, that's actually that's a damn good strat.
Help me make the world's strongest nitric acid. You see, the ozone gas it generates is much more chemically angry than even pure nitric acid, and when I use a calcium chloride filled wash bottle to try it and then lead it to my anhydrous nitric acid, it slowly reacts with any nitrogen dioxide present to form even more nitric acid.
There's the actual
In doing so,
formula
it
for
scavenges the last minute traces of water, and after roughly an hour of bubbling ozonated air through my nitric acid while keeping everything cool, the yellow color disappears.
Yeah, ozone's definitely something to be cautious of, given that it can, you'll smell pennies if you smell too much ozone.
The red fuming nitric acid, making almost perfectly pure white fuming nitric acid. Now, it's not 100% concentrated, since like all chemicals, it physically can't be, but doing all this work managed to remove so many contaminants, it's probably like 99.999% pure, and I might as well round it up to 100. It's really funny to think that this small amount of what looks like water is actually one of the strongest acids in its pure state, and since I finally achieved this holy grail of amateur chemistry, now it's time to do some experiments and compare it to all the previous levels of nitric acid.
Or are you gonna do something crazier with it?
First of all, this devil's water is definitely
it's already getting yellow.
more unstable than its predecessors, quickly going yellow without the ozone, which is why I had to be really fast with filming all the experiments. And for the first one, I just had to see what it does to nitrile gloves. As expected, pouring it over a glove
starts burning a little faster than the red fuming stuff.
And you can actually see the difference compared to igniting gloves with RFNA, which takes quite a while. I also recorded this cool slow-mo shot of pouring anhydrous nitric acid over gloves, and this way you can nicely see the evolution of nitrogen dioxide gas and a ton of this white smoke.
Really had time to get his hand away before it started burning.
The second reaction I wanted to showcase is how nitric acid interacts with iron in the form of this steel wool. Now, what is really quite interesting, dilute nitric acid dissolves it quite readily, and the azeotropic stuff just eats through it, while RFNA and anhydrous nitric acid don't seem to react at all. This is because when nitric acid contacts iron, a very thin coat of iron nitrate forms around the metal.
It's actually too good as an oxidizer, so it
dissolves, exposing more metal to
doesn't actually allow the ions to dissolve.
When there is little water present, the iron nitrate coating acts as a protective layer against attack, and this is why nitric acid is often transported in steel tanks. What's quite peculiar about this protective nitrate coat, however, is that at high temperatures, nitric acid just says no
It's
to
still
it
an
and
oxidizer though, so
explosively
you can still
oxidizes
burn
and
it.
the iron
The
metal
melting
beneath to
steel
form
also will
iron
allow you to
oxide.
expose
This
more
also
steel to more
creates
nitric
enormous
acid.
clouds of nitrogen dioxide and generates enough
Who needs
heat
water
to
when you can
melt
just burn it
everything into
instead?
these
Melt
glowing
it.
blobs. Again, I think that anhydrous nitric acid performs quite a bit better when compared to RFNA, and the slow-mo shot of this reaction is just gorgeous. This protective nitrate coat formation not only applies to iron, and other metals like copper also resist reacting with anhydrous nitric acid. This also proves that the acid I made is really anhydrous, since the addition of just a tiny bit of water causes it to violently react with the copper. The same cannot be said for RFNA, which has enough water to react with copper by itself to some extent, proving that even 1% of water can drastically change nitric acid's properties. Anyway, for the next experiment,
copper's also a lot
I
more
decided
active
to
than
go with a classic and
iron as well.
showcase
It's
the
more
rocket
readily
fuel
able
part
to
of nitric acid, which
give up
being
its
a very
electrons,
strong
so even just a 1%
oxidizer,
of
easily
water,
reacts even
make it
with
work
weak
even
reducing
the
agents like
RFNA didn't
aniline.
work with the steel
As you
wool.
can see, the two generate this weird tar on contact and let off a ton of gas, which sometimes
hypergolic
self-ignites,
reactions.
creating
Reactions that
this funny
explode.
sound. This is known as a hypergolic reaction, where the fuel and oxidizer ignite spontaneously on contact, and reactions like these using pure nitric acid and some more exotic chemicals than aniline are the basis of many liquid propellant rockets. When I tried this reaction with RFNA, it also formed a bunch of tar, but didn't really want to ignite, and the azeotropic nitric acid barely did anything to the aniline, turning
It'll
it
get
light
spicy,
brown.
but it won't actually
What's quite
light a
interesting
fire.
is that the poor man's nitric acid seemed to react quite differently, forming this white precipitate, and this is because, being so dilute, it can calmly react with aniline to form a salt called aniline nitrate. Overall, I think that this project really turned out cool, and it was certainly nice to explore the less known aspects of nitric acid, and it also made for a nice starting point for future projects where I will be able to use all the different grades of nitric acid I made. Speaking of future projects, for the last month I have been hard at work at recording my most complicated video.
Alright, I think we're getting towards the self-promo section of the video, but alright, I think that's gonna do it for me. We saw some cool stuff today. We saw an Australian man working in a horrible dilapidated shed with a lot of lead and making some cool glowy things, and we got to see some stuff catch on fire with this really ultra pure nitric acid. So I don't know, I was entertained. I'm excited. Thanks for vibing out in the background with me, y'all. Hope you enjoyed some of the chemistry chatter that I like to do with this little spontaneous video that popped up. So yeah, we'll be back on Monday, Tuesday with more Mega Man Powered Up. Planning on finishing the rest of Time Man, and then also doing a little bit of Time Man's challenges as well, just to fill out some of the time, because I doubt the rest of the Wily Castle is going to take 2 hours. And then more Freedom Planet on Tuesday. So yeah, thanks for joining me, everybody. Dilapidated shed with a lot of lead. That's a hard ass bar. It's pretty good. Ironically, considering lead is very soft, for a metal. But yeah, have a good night, everybody. I will talk to y'all later. Like the video and all that just interactive stuff to help me out. Join the Discord if you like. We talk about mostly gaming there. But you can always throw in some chemistry if you're interested. So yeah, have a good night, everyone. See you next week. Bye bye.